So in this chapter, we're going to be talking about rational functions, and so we're going to be hitting on SOCL number 4. We're going to be talking about characterizing vertical and horizontal asymptotes of rational functions, find the equations of asymptotes of rational functions, graph and analyze a rational function by using transformations, sketch the graph of a rational function, analyze the domain, range, asymptotes, intercepts, and graph of a rational function, and construct the equation of a rational function given the graph. So we're going to first define what a rational function, and we're going to apply notation describing the infinite behavior of a function. So let p of x and q of x be polynomial functions where q of x is not equal to 0. A function f is defined by f of x equals p of x over q of x is called a rational function. Notation, x approaches c from the right but not equal to c. So instead of going to positive, like positive and negative thing, we're thinking of actually approaching a physical number. So this would, like said, let's say if this said x approaching 1 from the positive side, that would mean that we're taking numbers like 2, then 1.5, 1.4, 1.3, 1.2, 1.1, 1.01, 1.001, getting closer and closer from the right side. And this would be then x approaches c from the left side. So like 0.99, 0.999, 0.99999, keep getting closer to that 1 without ever equal to it. Of course, you already know what this one, as x approaches infinity, we sometimes say x increases without bound. X approaches negative infinity, x decreases without bound. So let's look at an example. The graph of f of x equals x minus 1 over x minus 3 is given. We want to complete the statements as x approaches infinity. We'll notice that x approaches infinity, my y value approaches this line, 1. As x approaches negative infinity, same thing happens here. My line approaches from underneath it, but it still approaches y equals 1. As x approaches 3 from the positive side, well, my y values are shooting up to infinity. And as I approach 3 from the negative side, my y values are going to negative infinity. So restrictive values. The restrictive values for rational functions are any values that make the denominator 0. To find the restrictive value, set the denominator equal to 0 and solve. So on this last example, notice if x equals 3 here, that would make my denominator 0, which makes it undefined. So my restriction value here would be 3. And so the way we find that the restrictive value is we just set the denominator equal to 0 and solve. And then we want to talk about identifying vertical asymptotes. Vertical asymptote line x equals c is a vertical asymptote of the graph of a function f if f of x approaches infinity or negative infinity as x approaches c from either side. So like here, this would be a vertical asymptote because when we approached x equals 3 from the right side, it went to positive infinity. When we approached x equals 3 from the negative side, it went to negative infinity. Here's some more examples of vertical asymptotes. It could look like this. It can look like that. It might look something like this or like that. These are all instances, and it only has to be on one side. I mean, I may not have enough over here. As long as I'm on one side, I'm approaching negative infinity. As I get closer to x equals c, that's going to be a vertical asymptote. So we let f of x equals p of x over q of x, where p of x and q of x have no other common factors other than 1. To locate the vertical asymptotes of f of x, set the denominator equals 0 and solve. So here we want to identify the restrictive values, we want to identify the domain, and then the vertical asymptotes. So Here, x cannot be equal 5, so my restrictive value here would be x cannot be equal to 5. Means my domain here is all real numbers except for 5, so the way we would write our domain we go to negative infinity up to 5, parentheses union 5 to infinity. And my vertical asymptotes, since nothing reduces here, then my vertical asymptotes would be x equals 5. And I'm going to abbreviate vertical asymptote from here on out as VA. So when you see VA, it's not for Veterans Affairs, it's for vertical asymptote. All right, so looking at number 3, first I would need to factor that denominator. So looking at that denominator, I'm looking for factors of negative 3 that add up to negative 2. So that'd be 1 and negative 3. So I have two restrictive values. Here x cannot be equal to negative 1 and x cannot be equal to 3. That means my domain here is going to be a little bit more complicated, because I'm going to have to remove both those values. I'm going to have to remove negative 1 and 3 from the real numbers. So that's going to give me negative infinity to negative 1, parentheses, union, parentheses, negative 1 to 3, parentheses, union, 3 to infinity. Now, in terms of my vertical asymptotes, just to kind of be very clear here, when I'm finding the vertical asymptotes, I have to make sure P of x and Q of x have no common factors other than 1. So here, if I go back up here, I can actually divide out the x minus 3's. That leaves me with 1 over x plus 1. So x minus 3 is not going to give me a vertical asymptote of x equals 3. In fact, if you were to graph it, it would look exactly like the graph is 1 over x plus 1, except you would have a hole at x equals 3. So my vertical asymptote, I'm just going to get 1 from that denominator. That's x equals negative 1. All right, let's try this next one. Here we got to do some factoring. Looks like I need a little space here, so let me just mark it. And let's go ahead and factor this. So I'm going to group the first two terms together and the last two terms together. First two terms have a common factor of x squared. Last two terms have a common factor 25, but I'm going to factor out negative 25. And let's see if I can write that a little bit better. And then my two pieces have a common factor of x plus 1, or sorry, x minus 1, excuse me. My leftovers are going to be x squared minus 25. But then, we can factor that into x plus 5 times x minus 5. So in terms of my restricted values, I'm going to have three restrictions. X cannot be equal to 1, x cannot be equal to negative 5, and x cannot be equal to positive 5. Those are my three restrictions. So my domain is going to be very complicated because now I'm going to have three holes. I have one at negative 5, 1, and 5. So we go from negative infinity to negative 5, then from negative 5 to 1, and then from 1 to 5, and then finally 5 to infinity. Now in case when this is factored here, none of these factors are in common with that 3x minus 1, so they're not going to be able to reduce here. So we're just going to leave that in factored form. I guess I should have written it up here. So there's nothing I can reduce here. So I'm going to get three vertical asymptotes. We're going to have one at x equals 1, x equals negative 5, and at x equals 5. So let's go ahead and look at number 5 and 6. Now, here we're determining the domain of the function interval notation. So I'm not going after vertical asymptotes or anything. All I'm looking is at the denominator. Here we have x minus 9 in the denominator. I don't care if it reduces here because I'm just doing domain. X cannot be equal to 9. So my domain here would be from negative infinity to 9 union 9 to infinity. I don't care if anything reduces or not, because all I'm going after here is the domain. Now in reality, if you factor that numerator, those would reduce and you would just get x plus 9. And so what your graph actually would be a linear equation. It would look exactly like the linear equation except at 9, x equals 9. So it's going to look something like this. But what's going to happen here when we get up to 9, there's going to be a hole in the graph because that's where the function's undefined. Again, we don't need to worry about this. We were just going after the domain here. Let's try this next one. Again, not concerned about the numerator, denominator. That's a difference of squares. That factors into x plus 4 times x minus 4. So my x here is not allowed to be equal to plus or minus 4. So in terms of my domain, it's negative infinity to negative 4, union negative 4 to 4, union 4 to infinity. And that would be my answer. Now again, you may notice that the x plus 4s would divide out if we continue the problem, which we don't because we're just getting the domain. So in terms of this graph, this would be the graph of 1 over x minus 4 if you cancel those out. We'd have a vertical asymptote at x equals 4, and then there would be a hole at -4.